Hey everyone, this is chapter 4, and now we're getting into some real heavy-duty chemistry in this chapter. It's called Atoms and Elements. And in this chapter, we'll look at how we read the periodic table, how we use it, and then also how we visualize atoms and the electrons and kind of how it all works. And so this picture is looking at a farmer and how he might use chemistry to do his job and use fertilizer. So a lot of different fields definitely use this information. Okay, our first term is element. So this is one term that you'll want to write down and know. Elements are pure substances. They're all made of one type of atom, like a chunk of aluminum foil, and they can't be broken down into anything simpler. You can break them down into individual atoms, but you can't break them down into different atoms. So they're all made of the same thing. Here are some examples of elements. You've probably heard of all of these: uranium, titanium, chlorine. They're named for different things. Some of them are named for people, planets, geographic locations, colors, minerals. So you can see some different examples here and what they're named for. Then we also have symbols for each of these elements. And these symbols are usually one or two letters. The first letter is always capital. So if they're a one-letter symbol, it's just a capital letter like carbon, nitrogen, fluorine, and oxygen. And then if they're two-letter symbols, the first letter is capital. You might see some periodic tables that have three-letter symbols like UUN. Those are some of the elements that haven't really been created or studied and not named yet, but they're coming up with names for them. So those are kind of the not quite named elements. Some of them are obvious names and some are not, like gold is AU and silver is AG and tin is SN. So sometimes they're not as obvious as the others. Here are some common ones, and this table is nice because it's in alphabetical order. So you can see the name and the symbol, and you can see some that aren't very similar. Like, let's see if I can pull one out. Cu is copper, so that one's kind of weird. Hg is mercury. Sodium is Na for natrium, and so some of them, they use the Latin and Greek words for the symbols. And then also notice that some of them are similar, like barium, boron, and bromine, and they have different names. So this is a handy table to bookmark. Here are a couple examples of the Latin names. So silver is Ag, named after Argentum, and then gold is Au, named after Aurum. So there are different ways that they're named. There isn't really like a standard system. They just kind of develop over time. All right, let's see if you can get this learning check correct. Pause the video and then I'll show you the answers. All right, there they are. So those are some names you should know. Probably about the first 20 or 30 are the ones that you're going to know well. You don't need to memorize them because you'll always have a periodic table with you. But just from use, those are the ones that you'll get to know better. Let's try these. These are symbols. See if you can name them. And you can try doing them from memory and then see if you get them right. And there are the answers. All right. So now we'll move into section 2. Section 2 is on the periodic table, so I'll kind of show you around and how to use it. The periodic table is man-made. That's probably the most important takeaway. And it's just our way of organizing all of the 118 or so known elements in the universe. And so sometimes it doesn't really make sense. Sometimes the rules don't follow their exceptions, and that's just because we're trying to fit nature into our own patterns with this table. But these are arranged by order of increasing atomic mass. So they're getting bigger as you go across. Hydrogen's the smallest, and this one down here is the biggest. And then one thing to note is that notice, let me get my laser pointer here. Notice this one here, lanthanum, it has a number of 57. That's the atomic number. And then the next one, hafnium, is 72. And that big skip is because these two rows actually fit in right here, and all of these should scooch over. So they should actually scooch way over here. But if they did, then the table would be really wide. So they just kind of cut them out and stick them down here so that the table fits a little better. Notice also in this table that The blue ones are all metals, and then the green ones are metalloids, and the yellow ones are nonmetals. And then over here we have hydrogen. They also have labels like alkali metals, alkaline earth metals, halogens, noble gases, and then they have different group names. These are the transition elements. I have my students with a black and white version, and they color this in and label everything. So that might be a good idea to do, or even just like a sketch where you're labeling and color coding all of this, so you know which ones are the metals, metalloids, and nonmetals. Notice that most of the table is metals. So that's the left side of the table. Most elements are metals. So in the periodic table, we arrange them according to properties. So they actually make sense. They're not just randomly stacked in the table. We have groups, which are the vertical columns, and so those are going up and down, and those all have similar properties. So if you go in group 1, the first group with the hydrogen, hydrogen's group all has similar properties. Hydrogen's a little bit different from the others, but the other ones all have similar properties. And then the periods are the horizontal rows that go across, and they don't have common properties, but they're similar in other ways. And we have 7 periods as you go across the periodic table. So it's kind of like latitude and longitude. So here they are again. The groups go up and down. All of these, starting from lithium down to francium, have similar properties. Beryllium down to radium, same thing. They have similar properties. We usually skip the transition elements when we're learning how to use it. And then we skip over to boron. Carbon is all similar. Nitrogen all the way down is kind of similar. Oxygen, fluorine, and down, these are known as the halogens. And then the noble gases, which you've probably heard of. And then as we go across, these are the periods. So you have 7 periods. Here they are being counted all the way down. And then these are snuck in here. These are from period 6, the lanthanides, and the actinides are from period 7. So those are not like 8 and 9. They stick in right there. Okay, the group numbers are numbered in different ways. We use groups 1A through 8A for what we call the representative elements, and then we use B's for the transition elements. So those are the ones we kind of skip. Those are named 3B to 12B. In some periodic tables, you'll see that they're numbered just 1 through 18 straight across. There are 18 different groups in the periodic table, so it just depends on the table that you're using. And then, of course, the periods are numbered 1 through 7. So here, this is again, the representative elements are the ones that are colored here. We kind of ignore the transition elements when we're learning basic chemistry. We use these later. But we have groups 1A, 2A, 3A, 4A, 5A, 6A, 7A, and 8A. And you can see that these are all skipped, but these would be 3B through 12B. And the first group is called the alkali metals. Second group is the alkaline earth metals. And then 7A is the halogens, 8A is the noble gases. These don't really have names. Okay, so here's some notes about some of these groups. The first group is 1A. These are the alkali metals, and they are lithium, sodium, potassium, rubidium, and cesium. Hydrogen is right above, but it doesn't really count because it's not a metal. It's a nonmetal. These are really interesting metals in this group because they're super reactive. They're the most reactive metals on the periodic table. They're reactive because they have one outer electron, and they really want to get rid of it. So all of these, if you were to drop them in water, they would react and start fizzing and maybe even light on fire. And you can Google some YouTube videos like that. In class, I always demonstrate this with sodium with my students, and we drop some in water and usually have quite a show. This sodium is what you're eating in salt, basically, but you're eating the ion form of this. So you're eating, when you sprinkle salt on your fries, you're eating the ion form of sodium and the ion form of chlorine. But when it's just plain sodium and it's not ionized, it's actually less stable, and it looks like this soft metal, and you can actually cut it with a knife. It's kind of like cold butter. That's the consistency of it. Group 2A are called the alkaline earth metals. They are also metals. They're not as reactive. because they have 2 outer electrons that they're trying to get rid of instead of 1. So these are beryllium, magnesium, calcium, strontium, barium, and radium. You've probably heard of these 2. You might take them in your multivitamin. And some of these are used for fireworks because they burn at different colors. And you'll have a lab, if you're in the lab class, you'll have a lab burning different salts. And these salts are similar or exactly the same as what they use in fireworks. Finally, group 7A or 17 is known as the halogens. These are also very reactive. These are nonmetals, and they're the most reactive nonmetals. Fluorine is actually the very most reactive nonmetal, and then it goes down from there. And astatine isn't always considered in that list. This is what they look like. This is chlorine gas. It's a green gas. This is what you bond with sodium. Both of them become ions, and that makes table salt. But table salt looks nothing like a green gas or a silvery metal. And then you have these 2 gases also. All right, let's see if you can identify which element this is describing. So this one is group 7A, period 4. So kind of use your periodic table like a battleship, kind of like a grid, and try to find which one would be group 7A, period 4, and then find those 2, and I'll show you the answers. There they are. Okay, now let's look at the different types of elements. So again, you have the blue ones are metals, and then you can see this little staircase that's kind of between the metals and nonmetals, and those are called metalloids. So some, not all, but some of the ones that are on that staircase touching it are metalloids. And then the nonmetals are the ones on the other side, plus hydrogen, which is over here. So let's look at some characteristics of metals and nonmetals and metalloids. Metals, except for hydrogen, are on the left side, and most of the periodic table is metals. Some of their characteristics are that they are shiny, ductile, and they conduct heat and electricity. And most of them are solids except for mercury, which is a liquid. So you can see silver there is an example of a metal. And then nonmetals are on the very right side of the periodic table, and they are dull, brittle, and poor conductors, but they're good insulators. So sulfur is an example there. And they have low densities and melting points. And then metalloids are located along that zigzag step line that I showed you, except for a couple. And they have the properties of both metals and nonmetals. They are better conductors than nonmetals, but not as good as metals. So they're kind of in between metals and nonmetals. And they are used as semiconductors and conductors. So you'll see them used a lot in technology. Okay, here's some examples, a list of like silver, antimony, and sulfur, and you can see some different characteristics of them, and you can kind of get a comparison there. All right, so let's see if you can identify these 5 as metal, nonmetal, or metalloid. And there's your answers. And then can you list all of the elements that match the description? Okay, those are the ones that match that description. All right, so hopefully you're getting comfortable with using the periodic table a little bit. Here's a chemistry link to health. A lot of you are nursing majors, so it's important that we connect this to your major and your future career. Of all of the 118 elements, actually only 20 are required for life for humans, and 4 are the most important ones that make up our body mass. So oxygen, carbon, hydrogen, and nitrogen. And you can remember the acronym CHON, like CHON. Those are the ones that make up most of our body mass, and then the other ones are trace elements. And then most of us were actually made of water. These are the macro minerals that we need. So these are some of those other 20 elements that you eat in your food, and you might take a multivitamin: calcium, phosphorus, potassium, chlorine, sulfur, sodium, and magnesium. And this is what they're important for. So we need them for our bones and teeth. We need them for our heart and blood vessels and muscle contraction, nerve impulses. That has to do with your electrolytes, which is what you drink in Gatorade, and then also your acid-base balance and regulating how your cells do metabolism. All right, so here they are. These are the most important elements in your life, in your body. It has these color-coded, so you have the major ones, C, H, O, N. You have the macro minerals, so these four and these over here. And then you have some micro minerals. We just need trace amounts of these. So some of those should look familiar. All right, let's move into section 3. Let's look at what the atom is made of. So the atom is the smallest particle of an element that contains all the same characteristics of that element. It's not the smallest particle, though. We have particles that are smaller, like electrons, protons, and neutrons, and we even have particles that are smaller than that, like quarks. But when they get smaller, they don't have the same properties as the element. So like this is aluminum foil. It's only made of aluminum atoms. So these are representing aluminum atoms. They don't actually look like balls necessarily. But this is the smallest particle that's going to retain all the properties of it. And if you get any smaller, like to the protons, electrons, or neutrons, it's no longer going to act like aluminum. Dalton was the one who came up with this theory, but there were people before him, thousands of years even before him, that were starting to think like, hey, if you take a material and rip it up into enough little pieces, you're going to get to like its smallest particle, and that's basically what Dalton said. So these are the parts to Dalton's atomic theory. He said that atoms are tiny particles of matter. The word atoms comes from the Greek, I think, atomos, which means indivisible, which isn't really accurate because atoms are divisible. That's how we get electricity to charge our phones and how we get like radioactive decay and things like that. But he was mostly right. It was a start. He also said that the atoms of a single element are similar to each other and different from other elements. So like an aluminum atom is different from a gold atom. And then he said that two or more different elements can combine to form compounds. So you can put different atoms together and form different compounds. And when we have a chemical reaction, these are rearranged. And then he also said they're never created or destroyed. They just change places and change bonds in a reaction. These are the parts to an atom. These are the subatomic particles. Atoms have protons and neutrons in the middle. Protons have a positive charge. Neutrons have a neutral charge. And then electrons are in the electron cloud around the atom, and they have a negative charge. And like charges repel, just like a magnet, and unlike charges attract. That's really important for how atoms bond. So you can see here it's showing protons repelling, electrons repelling, and then unlike charges attracting. One of the famous experiments that led to us learning more about atoms was J.J. Thompson, and he was the one that discovered electrons. He built this cathode ray tube, which was the same tube that was used in really old TVs, like the big box TVs. And basically it was a glass tube with electrons shooting through them, but they didn't actually know what was shooting through them. So they had invented cathode ray tubes, but they didn't know what was in there. And so he figured out that they were electrons and that they were negatively charged and that they were smaller than an atom, which was crazy because back then, they didn't think there was anything smaller than an atom. So he proposed what we call the plum pudding model. I kind of think of it as like the chocolate chip model. It was wrong. He said that the protons and electrons were just like evenly dispersed. So like the protons would be the cookie and the electrons would be the chocolate chips. And that's what it looked like. So I think it looks more like a chocolate chip cookie. But he was wrong about this. It did support the cathode ray tube experiment. So he saw negative electrons shooting through the tube coming off of like metal. So he just thought they were like embedded in the positive part and that it was overall neutral. Then a guy named Rutherford came up with this famous gold foil experiment. So what he did was he took foil paper, really thin foil, kind of like aluminum foil, but made of gold. You might have heard of gold foil on like cathedral walls. They put gold foil. He shot alpha particles, which are basically they're basically 2 protons and 2 neutrons. It's a helium nucleus. He shot it at a piece of gold foil. Most of these alpha particles shot straight through the gold foil, but some of them bounced off at like these really extreme angles. So what he figured out is that the gold atoms actually have like a really dense little tiny nucleus, and these helium nuclei, the alpha particles, were bouncing off the nucleus. Most of the time they were passing right through because most of the atom is empty space, but he found this really dense positively charged nucleus because it was repelling the positively charged alpha particles. So this is what his experiment looked like. He had his gold foil right here. Out of this, these particles, these alpha particles, are actually radioactive. So this is where they came out of. So he shot a beam of these particles. These are positively charged little nuclei that he shot out. Most of them, let's look at this picture. This is zooming in to like this is one gold atom. Most of them passed right through because most of the atom is empty space. But some of them hit the nucleus of the gold atom and bounced off at these really extreme angles. And he had this like film, kind of like old camera film, to collect these little particles so they would hit the film and he'd be able to see where they hit. So he would see that most of them passed right through, but some of them bounced off, and he did all this math, and based on that he found that most of them were that there was a really dense nucleus that they were hitting off of, and that it was positive. So from that, they found that there was a nucleus at the center of the atom. Later on, they discovered neutrons. So that was Chadwick who discovered neutrons, and they found that there were protons inside that were positive, and that most of the atom is empty space, but that the electrons are in a cloud around the nucleus. And when I teach this to my students, I take them out on the football field, and we use different things to model like protons and electrons, but the nucleus stands in the middle of the football field. And then I have students who are representing the electrons, and the closest shell for the electrons is all the way at the end zone. So all of that space, so imagine like students standing in the middle of the football field and then students standing at both end zones. That's how empty the atom is. It's mostly empty space. That's why most of those particles shot right through the gold foil, and then a few of them hit that little center. So this is kind of a zoom in of a lithium atom. You can see that lithium metal is made of a bunch of atoms, and then if we zoom into the atom, we can see this super dense, teeny tiny nucleus with these electrons around it. And so most of this is empty space, and then you have the tiny, dense nucleus in the middle made of neutrons and protons. Remember, the neutrons are neutral, and the protons are positive, and the electrons are negative. Now we need to look at the size of these. So we use these, we don't use like we use atomic mass units a lot of times for chemistry because it's like a standard unit instead of using like grams, because it would be like 10 to the minus 10 grams. And so they use AMU, and it's 1/12 the mass of a carbon-12 atom, which has 6 protons and 6 neutrons. So 1 AMU is basically the mass of a proton. So you can think of it like that. AMU is the mass of a proton. We use Daltons in biology too. Electrons are super, super tiny compared to the mass of a proton. They're like 1,840 times smaller than the mass of a proton. So they're 1,840th of an AMU. And then protons and neutrons are roughly the same mass. So protons and neutrons roughly weigh the same as an AMU. Here is what that looks like in a table here. So you have protons have a +1 charge. Their mass is about 1 AMU. They're in the nucleus. Neutrons have no charge. They also weigh about the same. Electrons are teeny tiny. They have a mass of -1. It's completely opposite of a proton, but they weigh way, 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 way less. So like if your proton was a textbook, an electron would weigh like a piece of paper out of the textbook. Like it's way, way, way smaller. So let's see if you can identify which one fits the descriptions here, and then I'll show you the answers. There it is. Hopefully you're getting these right. Hopefully this is a little bit of a review. And let's move on to section 4. So now we're actually going to use the information that's on the periodic table, some of those numbers, and figure out what that's for. So in this section, we'll learn about atomic number and mass number. These are two numbers that are on most periodic tables. Some periodic tables have more information than that, but this is like usually the minimum information along with the symbol and name. So here's what this looks like. In this little periodic table block, you will see the symbol, you'll often see the name, and then you'll often see two numbers. This is only showing one of the numbers. This is the whole number, and it's also the lower number of the two. And this is known as the atomic number. This actually tells you how many protons there are in this atom. So sodium will always, this is sodium, Na, and it will always have 11 protons. So here are some examples. You can check out your periodic table as we look at these. Hydrogen is that one in the left corner. It has a 1 for the atomic number. That means it has 1 proton. Carbon has 6 as its atomic number, so it has 6 protons. Copper has a 29, so it has 29 protons. So here's some more examples. Lithium has a 3. Carbon has a 6, so they're located here and here. This is what they look like. And then you can see here that lithium has 3 protons, the red things. And it actually has 4 neutrons. Sometimes it has the same number of protons and neutrons, sometimes not. It also has 3 electrons. The reason it has 3 is because the 3 electrons are canceling the positive charge of the 3 protons. And then if we look over here, this is carbon. It has 6 protons. It also happens to have 6 neutrons. Some don't have equal numbers. And then it also has 6 electrons to cancel the positive charge of the 6 protons. So usually for a neutral atom that is not an ion, for a regular neutral atom on the periodic table, the number of protons is the same as the number of electrons. So here's an example. Aluminum has 13 protons and 13 electrons. So overall, those charges are going to cancel. 13 positive, 13 negative, 0 net charge. So overall, they have a 0 charge. Let's see if you can fill this in, find nitrogen, zinc, and sulfur, write its atomic number and the number of protons and the number of electrons. Let's see if we can do that. And there's the answer. Hopefully you got those right. Now we're going to look at the other number that's on each block of the periodic table, and that's the mass number. This is the bigger number, and this says here that it's always a whole number, but some periodic tables, it has a decimal. So in yours here, it'll have a whole number, but sometimes it's written as a decimal. If it's a decimal, then you just round it. You use normal rounding rules and just round the number to a whole number. The mass number tells you the number of protons plus the number of neutrons that are in the nucleus. So it's kind of like the mass of the nucleus measured in AMU. So here's some examples. You have hydrogen has an atomic number of 1 and a mass number of 1. That means that it has 1 proton, 1 electron, and then if this is protons plus neutrons, then it has 0 neutrons. Let's look at this next one. Nitrogen has an atomic number of 7 and a mass number of 14. So this 7 atomic number means it has 7 protons and 7 electrons, but then it has, we go 14 minus 7 is 7, it has 7 neutrons. Let's do one that's a little different. I'm going to look at chlorine here. Chlorine has an atomic number of 17 and a mass number of 37. So the 17 means that it has 17 protons and electrons, but then we take 37 minus 17, and that's 20 neutrons. So sometimes the protons and neutrons are the same, like these, and sometimes they're different, like these. So you just have to do the math to find the number of neutrons. Mass number minus atomic number. So here's your formula. Number of protons is atomic number. Number of protons plus neutrons is mass number. So if you want to know how many neutrons, you subtract mass number minus atomic number. Try this one. See if you can look at lead, has a mass number of 207. Find out how many protons, neutrons, and electrons it has. And there is your answer. And it shows you how to do it too. All right, now we're going to look at what we call isotopes and atomic mass. And so on the periodic table, what we show with the atomic mass is the normal, average, most common form of that element. But there can actually be different forms. Sometimes they're what we call radioactive. So maybe you've heard of radioactive isotopes. And they can have different numbers of neutrons. So that's what we're looking at in this section. This is an example here. This is magnesium. It has atomic number of 12 and atomic mass of 24. So that's what those two numbers are. And this is how we write them. So let's first look at what an isotope is. An isotope is an atom that has the same number of protons, but it has a different number of neutrons than the one that's put on the periodic table. Or it's just a less common one. So the ones on the periodic table are also isotopes. They're just the most common isotope. So it has a different mass number, but it has the same atomic number. So here's an example, 12 and 24, and that is magnesium. So here's a couple examples that we can try to solve. This is oxygen. This is how we rate these. Another way that we kind of abbreviate them to show the atomic number and the mass number. So the bigger number always goes on top. That's the mass number. So this oxygen has 8 protons, 8 electrons, and 16 minus 8 neutrons. And you can check your periodic table to see if this is the same as what you see on the periodic table, and it should be. And this one has 15 protons, 15 electrons, and 31 minus 15, neutrons. And then zinc here has 30 protons and 30 electrons, and then it has 35 neutrons. So make sure you know how to do those. And here, this shows kind of that math of what we just looked at. So now let's look at what we actually see on the periodic table if it's showing decimals. We actually see this number 24.31 instead of just a 24. That's because to find the mass number, they're actually taking all the naturally occurring magnesiums and they're weighing them and averaging them. And they're finding that it's not exactly 24, that there are some magnesiums that are slightly different. Most of them are like this, but some of them are different masses, just less of them. And so it makes this what we call a weighted average of different from 24. So here's some examples. These are isotopes of magnesium. Usually 78% of magnesium is like this, but sometimes it has, let's see here, see this extra neutron? So it has 13 instead of 12, and that's going to affect the mass number, but everything else stays the same. And sometimes, rarely, it can have even more, 14 neutrons, so it affects the mass number. So that's why your weighted average is 24.13 instead of just a flat 24. So that's what isotopes are. And some of these can be radioactive, and they can be used for different things like medicine. So let's try this one. This is a learning check. I want you to write how many protons, neutrons, and electrons there are for carbon 12, and it would have a 6 down here too. Let me just write that. So carbon 12, carbon 13, also 6, and carbon 14, also 6. So go ahead and write your answers down. And there they are. So they all have 6 protons, 6 electrons, but the difference is the number of neutrons. And this is like a carbon-14 that they use for carbon dating. What about this? Can you write the atomic symbols showing the atomic mass and the atomic number for each of these? You'll use protons to figure out what element it is, and then you'll add these two together to find the mass number. See how you do. There you go. So you have those 3 examples, and that's how you write them. And then what about this? Can you identify which pairs do both atoms have 8 neutrons? So which pairs have that? And which of the pairs below are of the same element? So let's see if you can answer those 2. I read those out of order. So it looks like B, the second one, is the same element, and C has 8 neutrons. Okay, so atomic mass is that weighted average. Atomic mass is a decimal. Some periodic tables will round it and have it as a whole number, like this here. You can see a whole number. The reason it's a decimal is because we're taking the weighted average of different isotopes, and we're multiplying it by the percent abundance of that isotope. So to calculate atomic mass, you have to know percent abundance, and then you multiply that by the atomic mass of each isotope and add them all up together. This is the same way that you do weighted average for like grades if your grades are weighted differently. So here's an example. If we're doing chlorine, you'll take the mass of chlorine, 3517, which is this guy, and then you'll multiply that by the percent abundance. So it's 75% abundant. You get this mass. And then you'll take the mass of chlorine 37, which is this, that's what it weighs, multiply it by the percent abundance. You get that number, and then you add those 2 together, and that's going to give you a weighted average. So instead of just taking the averages of these 2 masses, you get a more accurate average. And here are some different examples. So lithium exists in these 2 forms, these 2 isotopes. And this is the weighted average. This one's the most abundant. So you can see that 6.9 is pretty close to 7. Here's some different types of carbon that we've looked at. This is the atomic mass. It's pretty close to that 12. Here's oxygen. You can tell that it's pretty close to that 16. So this one's the most common one. Doesn't look like fluorine has any isotopes. For sulfur, this one's the most common one because it's close to 32. For potassium, that one's the most common one, close to 39. And then for copper, this one's more common than the 65 because it's closer to 63. So that's what the weighted averages look like for these different isotopes. Okay, so that's how we use it for lithium. Oh, whoops, that was a learning check, sorry. Hopefully you went back and paused that and answered that question. And you can see which one would be the more common one, the 7 instead of the 6, because the atomic mass is 6.9 for lithium. Let's try this one, and I won't blow through it. This is gallium, and gallium is pretty cool. You should Google some YouTube videos of it. It melts in like warm water, so there's some tricks where you take like a spoon that looks like gallium because it's a metal but almost a metalloid, and it'll melt as you're stirring your tea. So definitely look at some YouTube videos. It's kind of a cool trick. But if you have 60.1% of gallium-69 and 39.9% of gallium-71, can you calculate the weighted average of those 2 and find what the atomic mass would be of gallium? See if you can do that. And that's how you solve it. That's step 1, and then I'll go to the next slide. And your final answer is 69.72. So you add those 2 together. That's how you do your weighted average. Right. This is section 6, and this is when we're getting into electron energy levels. You might have learned about energy levels before, but we're about to get a little bit more complex than what you maybe have learned. And this also is about how light is made. So the way that light is made has to do with these energy levels. So we'll show you some of that. First, let's start with what electromagnetic radiation is. Electromagnetic radiation is light, but it's not just the light that we can see. It also includes light we can't see, like X-rays, gamma rays, UV light, infrared, microwaves, radio waves. Those are also all light. They're part of the electromagnetic spectrum, but we can only see the colors of the rainbow. And all light is made in the same way. It all has particles and waves, and it has characteristics like wavelength, amplitude. It can be high energy or low energy. High energy has short wavelengths, and low energy has long wavelengths. So here's that whole spectrum. All of this is light. All of it's the same, except it has different wavelengths and frequencies. So if we look here kind of in the middle, this is visible light, and if we zoom in, we can see a rainbow. This is what the human eye can perceive, but there's all these different wavelengths and types of light that we can't see. Some animals can see it, like pit vipers can see infrared. So if we start way over here, the light with the longest wavelength is called radio waves, and we use this for radios and cell phones sometimes. And then the next shortest is microwaves that you use for your microwave oven and your cell phone. All of those use microwaves. Some use radio waves too. And microwaves have a pretty long wavelength of like, I think about 10 to 20 centimeters. So the waves that your microwave uses are pretty long. They're too long to get out of the microwave. That's why they have little holes that you can see through in the microwave. And so these wavelengths are too big to hurt you. Infrared is heat waves. They're getting a little smaller. Visible light is even smaller. It's pretty minuscule. And then we get smaller and smaller and smaller. These are the ones that get harmful. So when they're super small, they can penetrate your skin and your cells and your DNA even, and they can mess you up. So that's why UV light from the sun, we use things like sunscreen and clothing to protect ourselves. If you're getting an X-ray, you sometimes have to wear like a metal apron over other important parts that you don't want exposed to X-rays, so that radiation. And then gamma rays are even worse. And so if you're in the medical field, you might be using or be exposed to even some of these types of rays, and we need to make sure that they keep you safe. So all light is the same, but we can just see that little tiny part of it. And we can also separate light into different colors. This is what a raindrop does, actually. When we have white light, for example, pretend this is white light coming from the sun, and it separates in a raindrop, then you see a rainbow. But if you just start out with one type of light, like burning barium, so here they're burning barium salt, it produces this green light. If you put it through a spectrum, it's only going to have certain wavelengths. And so you can actually look at barium's specific like signature if you look at it through a prism, and this is always what barium is going to look like. This is actually how they get information from space, from stars, because they can put it through a prism. They can put the light from a star through a prism and look at it, and they can tell what the star is made out of based on what it's burning. So this is called an atomic spectrum. We also have different energy levels that electrons exist in. So electrons are going around the nucleus in a cloud. They're pretty far from it. They're super tiny, and they exist in different levels. So they can be like in level 1 or level 2. You might have seen these as like shells on a model of an atom. And as they get further and further and further away from the nucleus, they get higher and higher energy. So it says energy increases. And we also know that this energy is quantized. That means that as they go up level to level, they're going to gain a certain amount of energy, and it's a specific quantized amount. And as they come back down, they're going to lose a certain amount of energy. And it's always the same amount of energy. That's how they know that they're in shells, kind of. They're not just like smeared all over the place. They're in distinct like stories or layers based on how much energy they give off. So this is kind of what it looks like. They have to be on this shelf. They can't be in the middle in between shelf 1 and 2, or they have to be on this shelf. They can't be in the middle. And so as you get higher and higher up the energy increases, kind of like potential energy on a bookcase. And so pretend these are electrons sitting on the shelf. That's not really how they act. So as they change energy levels to go up from from level 1, let's say, to level 2, they have to absorb energy. So you have to excite the electron. And then when they go back down, they're going to release that energy that they had gained. So we know as they go higher, they have more energy. But if they are doing a bigger jump, like maybe they're going a couple levels, that's going to take more energy and they're going to give off more energy. And so that's what determines what kind of light it is. If they're just giving off a little bit of energy, I kind of skipped a step, hold on. When they make this jump down to a lower energy level, they're giving off light. So this is actually where light is made. Light is made when the electrons are jumping down a level. And if they jump down a higher level, then they're going to give off higher energy photons. So these are going to have a shorter wavelength like gamma rays. If they just go down a short distance, they're like radio waves. That's kind of an extreme example, but as you release less energy, then it's going to be like less energy light. And you can see it has its own wavelength, which is determining what type of light it is. Okay, so that's a little run through on how light is made, but now we're also going to look at how the electrons actually arrange themselves in the atom. So they're not actually in shells like they teach you in 8th grade or whatever, when you maybe last saw what an atom looks like. They're actually arranged in these sublevels. And these sublevels have different shapes. They're not actually all circles. Some of them have weird shapes. I'll show you in a second. And they have names. So these sublevels can be S, P, D, or F. The S is the lowest energy and the F is the highest energy. Okay, so on that first energy level, like the first shelf, you have one sublevel and it's only an S. It's an S sublevel. I'll show you what that looks like in a second. On your second shelf, you have two sublevels. One of them is an S, so now you have a new S, and you have P shells, P sublevels. When you get to the third shelf, you have three sublevels, and they can be S, P, or D. And then when you get to the fourth energy level, the fourth shelf, you can have four sublevels, and they can be S, P, D, or F. So that's kind of an overview of the sublevels and what's at each level, but it gets a little bit more complicated because we're trying to fit super complicated like nature and the universe into our heads and make it make sense. And sometimes it doesn't make sense that easily. Okay, so the S shells, those are the lowest energy ones. Every shelf has an S shell, even the bottom one. These are basically like spheres. So this is like how you probably think of an electron cloud, is just a sphere. And so it's just like a region of space that has the shape of a sphere, not spear. And this is where the electrons are probably found. So you have a high probability of finding electrons in this space. The problem with electrons is they're kind of crazy. They're like swimming around all over the, not swimming, but they're like zipping around. You don't really know where they are. If you find them, then you knock it off kilter and you don't know how fast it's going. So there's just a high probability that there are electrons somewhere in this space. This is the size of the first shelf. It's smaller. The second shelf is bigger. So the second shelf has also an S shell. And then the third shelf has an even bigger S shell. So as you go higher up, the S shells get bigger. So like kind of the balls get bigger. Okay, so those are S orbitals, S sublevels. And then you have P orbitals. I'll show you a picture hopefully in a second. But P orbitals are the next ones. They exist on energy level 2 and up. And they look like, they call them dumbbells. They look like two balloons, sorry, two balloons tied in the middle. And each little balloon can hold one electron. So the two balloons together can hold 2 electrons. I missed on the last slide that the s shell, the s orbital, just one s, can hold 2 electrons. And these can also hold 2 electrons. But they don't look like circles. They look like 2 balloons. And you have 3 of these possible, 3 of these double balloons. So you basically have the potential for 6 lobes on each shelf. You have one going in the X, Y, and Z directions. So here's what they look like. Do you see how they're like balloons tied together, tied in the middle? And they're going in the X direction, the Y direction, and the Z direction. Here they all are together. So wrap your brain around that. Try to picture them in 3D, like 6 balloons that are tied in the middle. And each of these lobes can fit 1 electron. So you can fit a total of 6 electrons here. That means, like, let's say we're talking about energy level 2. Energy level 2 has an S shell, and it can have 3 P shells. The S shell can fit 2 electrons, so I'm actually going to draw it here. So let's say you have your S shell. It would look like this. It would be a ball, and we would call it the 2S. And you can fit 2 electrons on the S shell, right? And then on your P shells, each of these, you can fit 1 electron. So if you count all these up, this is a total of 1, 2, 3, 4, 5, 6, 7, 8 electrons that can exist on this second shell. And then if we looked at the shell before that, we do have a 1s shell on that first shelf, and it can fit 2 electrons. So that means on the first shell, you can fit 2 electrons. On that second shell, you can fit 8 electrons. And you might have seen this drawn like this. Here's your first shell, 2 electrons. Here's your second shell, 8 electrons. So you might have seen it like this when you were in school. You might have heard this, that they can have 8 electrons. That might be familiar. But the second shell, sorry, can have 8 electrons. It's true, except they're not just on this circle. They're actually arranged like this, where you have 2 of them on the 2s shell, and then the rest of them are on these P sublevels, which are the P shells. So that's actually what an atom looks like. The D shells are a little different, and I'm not going to keep drawing these, but you can just think of this layering on and on and on like a whole bunch of flowers, like petals on a flower. You have 5 different types of D shells. Each of these can only fit 2 electrons. So you might have 1 electron here and 1 here. You might have 1 electron here. Oh, oops. And I'm trying to erase. Okay, I'm highlighting. Hold on. Okay. And maybe 1 here. And this one, you might have 1 here and 1 here and here and here, let's say. And then this one's weird. This one looks like a double pacifier, maybe there and there. So all total, imagine these all stacked together at once, like a big poofy flower, like all of these. That means that if all of these were filled up with electrons, you could have 10 electrons, because for each of these, you can fit 2 electrons on each of them. Okay, so that's a total of 10 electrons. The last ones are the F shells, and they're even wilder. I don't know if there's a picture of F shells. You can also only fit 2 on each of them, and there's 7 different F shells for a total of 14. So we have a couple of rules on how we fill up these orbitals. One of them is called Pauli exclusion principle. And each of these orbitals, like the s orbital, can only fit 2 electrons. So here's your s orbital. You can only fit 2. And we know that electrons repel each other, so these are both negative. They're going to repel each other. So if they are in the same orbital, they have to spin in opposite directions. So like this one's going to be spinning that way, and that one will be spinning that way. So they're like not in each other's business. They're not messing with each other. And we use these arrows to represent that. So we use like a down arrow and an up arrow to represent opposite spin. And here is another way to picture that. So they're spinning in opposite directions. That's Pauli exclusion principle. And here's the maximum that they can each hold. So that the S shells can hold 2. The P shells, you have 3 of them, can hold 6 total, 2 on each. The D ones, you have 5 different ones. They can hold a total of 10. And then the F sublevels, there's 7 different ones. They can hold 14. So here's another way to look at that. Your 1s shell can hold 2 electrons. Your 2s shell can hold 2 electrons. Your P shells, you have 3 of them, can hold a total of 6. So that means you can hold 8 on your second shell. And then again, you have a 3s shell with 2. You have your P shells with 6. And then your D shells, you can hold 10. Add all those up, your third shell can hold up to 18, and then it goes on from there. So you have your F shells too. So you get this learning check. Indicate the type and number of orbitals in each of the following energy levels or sublevels. So N equals 1 and the 3p sublevel. Okay, so the N equals 1 has just a 1s orbital, and then the 3p sublevel has 3p orbitals. All right, I think this is the last section. Electron configuration. So this is getting into a little bit heavier chemistry where we're actually using these shells and we're writing what we call electron configurations. This means that we're keeping track and figuring out where the electrons are in an atom. So this is where we identify the 1s, and then it goes to 2s, and then 2p, and then 3s, and on. So you can kind of see this pattern here. And this is where, like, these elements right here on the periodic table, they only have the 1s shell occupied by electrons. These have the 1s and the 2s. These have the 1s, the 2s, and the 2p shells occupied. These have the 3s and everything before it. These have the 3p and everything before it, and on it goes. And so we divide these up into blocks, showing like what's the last shell that's filled up. And they get filled up in that order, from the lowest shelf on the bookcase to the highest. And so we make these orbital diagrams to show which electrons are filled up. Okay, so remember they have opposite spin. This little box here is representing the 1s shell. And let's say we have 2 electrons in there. This one's representing the 2s shell. We have 2 electrons in there. This one's representing the 2p shell. We can have 6 electrons, but we only have 2. So what this atom would look like if we drew it in a simple way, we would have 2 electrons here, check, on that first shell. On the on the second level, I'm going to draw this simply, we have 4 electrons on this second level. So we could draw it like this. We have 4 electrons on the second level, just like that. But what we're actually seeing, if we're separating them by the orbitals, we're seeing our 2 electrons on the 1s shell. Then we have our 2s shell with 2 electrons, and then I'm going to use a different color. And we actually have a couple p shells. We actually have 2 of them. One of them has 1 electron, and the other one has 1 electron. So that's actually what this means. Like, here's one of them on the p shell, you know, and here's another one on the p shell, and then these 2 are on the s shell maybe. So that's actually what this is showing. And it's showing that we could fit we could fit a whole nother p shell if we had more electrons. We just don't. We don't have that many electrons. We only have, 6 total. So we don't need to fill up all the shells. So this is called an orbital diagram, and that's how we identify which electrons it has. And then we also use electron configuration to write the diagram we just wrote. And so we're using like these exponents and this weird code, but it's not really how they use exponents in math. So what we're showing here is that this is our 1s level. So this is basically showing that part of the orbital diagram. And this 2 here is just saying we have 2 electrons in that shell. And then our next level, our 2s level, so this is 1s. 2s has 2 electrons, again. And then our p shells, we have 3 of them. 1, 2, 3. They can each fit 2 electrons. And I think they did it with up arrows, it doesn't matter. And we're filling them like this. So we're not putting them together in that same thing because all of these are kind of at the same level. We load them all up at the same time, but remember they don't like each other. So we're going to spread those out. And then if we don't have room, then we're going to come back and put more electrons and load them up. We also use this noble gas notation, which is an abbreviated form. So you'll see that show up also. So here's an example. This is from the 1s block. Hydrogen has an atomic number of 1. That means it has 1 electron. So there's only 1 electron in that S shell. That's how we do the orbital diagram and the electron configuration. Helium is the next one. It has 2 electrons. And this is the orbital diagram and the electron configuration. And then these are some other ones. So this is from the 2s block. Notice that the 2s is the last one filled up in the 2s block. This is the orbital diagram, electron configuration, and then this is the abbreviated noble gas configuration, where instead of writing this part, we just write the last one, which is helium. So we put that in brackets, and then we write the rest of it. And that'll make more sense when we go with bigger ones. So this is our P block. That means that these are the last ones to be filled is the P block. And we fill them at the same time because the P's are all at the same level. So you're going to fill them in, and then when you run out of room, you're going to start doubling up. So you can see I'm doubling up here when I have to fill in my 8, 9, and 10 electrons total. This is how you write your electron configuration, and this is how you write your abbreviated version. So let's see if you can draw this one, and I'll do it with you. So nitrogen's atomic number is 7. That means it has 7 electrons. So we're going to fill up this orbital diagram. We'll use, and sometimes they're written like, oops, I didn't mean to do that. Sometimes they're written just with a little arrow like that. I think that last diagram had it, so you'll see that a lot. Or you can write the full arrow. So I'm going to put 2 of my electrons on the first shell. I'll put 2 more electrons on the second shell, and then I have to load these up together. So I have 3 more electrons left because I had 7 and I used 4. So I'm going to put 1 here, the next one here, and the next one here because they don't like each other and they're on the same level. So here it is kind of showing that slowly. You're going to fill up your first 2 shells doing opposite spin. And then your last ones you fill up like that, just like we did. Okay, so here's the 3s block. Your last one to fill up here is 3s, and this is the electron configuration. And then look at the noble gas notation. I'm using the last noble gas, and then writing the outer part, which is this last part. So that's why it saves room. This here is a lot shorter than this, and so I'm basically shortening all of this with my noble gas notation. So those are some more. And again, you have all of these are in the S block. That's the last block that you fill up. These guys are the D block, these guys are the P block, and these guys are the F block. Okay, so these are some rules on which ones are in each block, just kind of in word form, and what I just showed you, so you can summarize that in your notes. And then there's the F block. Okay. As we go above period 4, so we're on row 4, things get a little bit tricky. And that's because they kind of seem like they go out of order. So you can see here we're on potassium, happily going along, filling up these shells, then calcium, and then things get a little weird when we hit the 3D sublevel. So look at what happens. We're going with scandium here. We're going 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, and then we go backwards to 3d1. So what we do is we fill the 4s shell before we fill the 3D shell. And that's just because the 4s shell is more stable, lower energy than the 3D shell because it's weird. So make sure you know this order and the order that they're filled. And remember that you can put 10 electrons on your D shell because you have 5 sublevels. Also notice what happens here. You're happily going along filling the D shell, and then it takes one back from the S shell and puts it on the D shell. So sometimes weird stuff like that, it's kind of an exception, and things get a little funny. It happens here too. I missed that one. So instead of this being 4s2 3d4, it borrows one and puts it on that one. So it kind of gets funky sometimes, but that's how we do electron configuration, and that's how they fill up. And then after we fill up the 3 D10s, then we move on to our 4 Ps. So then we fill those up. So the 3D10 goes in between the 4s and the 4p. So it kind of interjects itself in. Here's a guide to how you write them. So those are some examples. So you can write some of that down. And it's showing at the period 4 level. So there's an example of selenium and how you write that one. There are also exceptions to the 3D sublevels. So here it is showing like sometimes it takes away that one from the 4s level and puts it over here in the 3D level. And then notice also that you fill these separately, all 5 levels, and then you go back and fill them. And this one's still left available until all of this is full. So there's just some weird exceptions sometimes. So let's do a learning check. See if you can identify the name of this, the element with this electron configuration, and take your time on this. Okay, so that element should be cobalt. And then see if you can write the electron configurations for these 3. And there they, oh, those are the locations. So first we have to find them. And then we are filling them with the electron configuration. So there they are. All right. Oh, last section. I thought the last one was the last section. So this is 4.8 trends in periodic properties. And when we're looking at the periodic table, we can actually see some patterns. That's why they put it in a periodic table. So one pattern that we look at is size. As we go down the periodic table, we can see that the atoms get bigger, and that's because we're actually adding shells as we get bigger, as we go across. And then you would think that they would also get bigger as you go across, but they actually get smaller. And that's because you are not adding any shells. These all have 2 shells, and they're gaining protons, and so those 2 shells, even though you're also gaining electrons as you go across, the shell is being pulled tighter because there's more protons acting on it and pulling it tighter. So here you're adding more shells, here you're keeping the shells the same, adding more protons, and it gets smaller. We also, when we study chemistry, we really only care a lot about the outer electrons in the atom. These are called valence electrons. The outer electrons are the ones that are going to be doing the bonding when you're bonding with other atoms. And so we only look at the valence electrons, and we can actually tell how many valence electrons there are based on the group number. So I'll show you what that looks like. These are all from group 1A. All of these have 1 outer electron because they have that 1s shell that's filling up on their outside, and they only have 1 electron that's going on that shell. All of these have 2 outer electrons because they're filling up that 2s shell, and then the p shells are underneath that shell. These all have 3 outer electrons because they're filling up the s shell and 1 electron in the p shell. These have 4. These have 5, these have 6, these have 7, and these have 8. All of the elements pretty much want to have 8 electrons on their shell. They want to have a full shell. So like if we look at this guy here, neon, he has 2 electrons on that S shell and 6 on the P shell. That means every spot possible is full of electrons. That's what all of them want. They're all seeking to have a full, all their shells full. Notice here that helium can only fit 2 electrons. So if he has 2 electrons, he's happy, he's full. But all of these are going to want to have that outer shell full. So we only care about valence electrons because they're going to be doing the bonding. Based on that, can you identify how many valence electrons these 2 elements have? And it's asking you for the valence electron configuration for these 2, and the group number and the period. So see if you can write those for calcium and lead. So calcium is in group 2A, period 4, and this is its valence electron configuration. So if you were doing noble gas, you would put the previous noble gas there, which is argon, I think, in brackets. And then this is lead. So lead is group number 4A, period 6, and this is its valence electron configuration. This guy is going to have 2 outer valence electrons, and this guy is going to have 4 outer valence electrons. Note here that it says that if the electrons are in the D or F sublevel, they're not considered valence electrons, and they usually are not involved with bonding. So we only consider valence electrons the ones in the S and the P shells. We also use what we call these Lewis symbols to identify how many outer electrons there are. So these are used to show valence electrons. Magnesium, for example, is in group 2, and it has 2 valence electrons. And so these are some ways that we can draw magnesium, showing that it has 2 outer electrons. We only care about those 2 electrons because they're going to be doing the bonding. So these 2 dots are electrons. If there are 4 electrons, they're shown as like 4 or less, they're shown as single dots. If there are 5 to 8 electrons, we usually put them as pairs next to each other. So here's some examples. Do you see here where nitrogen has 5, and so we put 2 of them as pairs next to each other? And you can see neon here is totally full. It can have 8 outer electrons, and it's set in pairs. So all of these want to be like neon and have 8 outer electrons. Hydrogen wants to be like helium and have 2 outer electrons. So that's how we draw Lewis structures. See if you can draw the electron dot symbol, the Lewis structure for these 3 elements, and I'll show you what they look like. So there they are, and you put them in pairs if you have more than 4. Okay, so we also look at atomic size, which is what I showed you on the first slide of this section, and we specifically look at radius to see how big the atom actually is. And so here's that picture again. As you go down, they get bigger. As you go across, they actually get smaller because that nucleus is sucking the shell tighter. And we can also look at ionization energy on the periodic table. Ionization energy is how much energy it takes to remove an outer electron. If we look here at sodium, sodium has all of this filled with electrons, and then its 3s shell is the outer shell, and it just has 1 electron hanging out there. So if I were to draw like a simple version of sodium, I would draw 2 electrons on that first shell, that's those. I would draw 8 electrons on the second shell. Remember, 2 of these are on the S shell, the other 6 are on P shells, but I'm just drawing a simplified version. So that's those, got all those. And then I'm going to have to add another shell because I'm out of room, and I'm going to put 1 electron on this shell. This is my 3s shell. Okay, so sodium is sitting here. It has 1 outer electron, and it really wants to get rid of that 1 electron. And so it's going to have a pretty low ionization energy because it's not going to take a lot of energy to get rid of that 1 electron. So here it is showing that. Do you see how that electron came off? And it's going to lose this shell altogether. So I'll erase that for you. This shell is gone. Now it actually looks like neon. And usually the ionization energy is low for metals and high for nonmetals because this guy really wants to get rid of that extra electron so it can be like a noble gas, like neon. And here's the trends for ionization energy. it gets lower as you go down and higher as you go across. So that's the trend for ionization energy. Metallic character is another characteristic that we can look at. And if it has metallic character, that means it's going to lose its valence electrons easily. So those that are alkali metals in group 1 are going to have a pretty high metallic character because they're going to easily lose their electrons, and then nonmetals are not going to have a high metallic character. And it decreases as you go down a group. So metallic character increases, and then it decreases as you get into the nonmetals. So they're more metallic this way, less metallic character that way. Here's a summary of the trends. So you have a nice table where you can understand what the trends are and the reasons why. Let's see if you can identify these three. If you have C, N, and F, which is the largest, which has the highest ionization energy, and which belongs to group 5A. And there are your answers. And let's see if you can answer these with increases or decreases. And there are your answers. This is a nice concept map summarizing everything that we learned in this very dense chapter. So take your time through it, go through this lecture again, go through your notes as you're working through your mastering chemistry. Make sure that you understand all these concepts well and ask me if you have any questions.